Lussacs law for your third and final gas law equation. So looking at our PTV card, the first gas law person that we had was Boyle. Boyle's law says that if we hold temperature constant, it's an inverse relationship. If one goes up, then the other one goes down. If one goes down, the other one goes up. The second gas law that we looked at was holding pressure constant. That was Charles' law. And we figured out with Charles' law, if the temperature increases, so does the volume. If the temperature decreases, so does the volume. So this is a direct relationship. If one goes up, the other one goes up at the same rate. It's a proportion. The third and final gas law person, if you look at the card, the only one that we haven't held constant yet is your volume. Sorry, wrong side. I'm looking at a mirror image. So we are going to hold our volume constant for this third and final gas law person. This third and final gas law person is, a lot of times people in the U.S. just say Gay-Lussac. It is French, so I've also heard people say Guy instead of Gay-Lussac, but it is a hyphenated last name. It's like Joseph Louis, I believe, is his first name. But he was a scientist, helped to discover boron. He proposed a new name for iodine, but he also looked at gases. And specifically with gases, he looked at hot air balloons. And when he was looking at those hot air balloons and everything, he used them to discover this third and final gas law, which had already kind of been used with Charles, with the hot air balloon aspect of it, as you saw in the demonstrations that were there. So what Gay-Lussac actually figured out was that pressure and temperature, just like volume and temperature, are directly related to one another, which this should make sense as well. As the temperature increases of the sample, the particles start moving around faster and faster and faster. As they move around faster and faster, you're going to have more collisions. The more collisions that you have, the higher the pressure. So as the temperature goes up, so does the pressure. If the temperature goes down, so does the pressure, because you're going to have fewer collisions. So when we look at our PTV card, we're going to hold our volume constant. And he is going to figure out that if the temperature goes up, so does the pressure. If the temperature goes down, so does the pressure. So this is another one that is a direct relationship, which also means that that direct relationship means that you have a proportion. So the equation for this one is going to look very similar to Charles' law. We're going to hold the volume constant, and we're going to take P1 over T1, pressure 1 over temperature 1, is equal to pressure 2 over temperature 2. Now, when we first made this card, we said that your pressure for that unit always has to be in ATM. So if you don't have ATM, you're going to have to convert it out, so you do. Temperature always has to be in Kelvin. So if you have Celsius, you're going to have to convert it to Kelvin. And your volume is always in liters, but we don't have to worry about the volume for this one because it is held constant. If you have 2 liters of gas, it'll be 2 liters of gas through the whole thing. If you have 30 molecules of gas, you have 30 molecules through the whole thing. So with your equation, again, I've got my document camera that we're going to switch over to, and we're going to do these 2 practice problems for the math. And then you should be good to go. So the equation that we have on this one, sorry, I'm trying to move it up a little bit. You have P1 over T1 is equal to P2 over T2. So with this equation, if I don't have my temperature in Kelvin, Kelvin is equal to Celsius plus 273. And then if I need to convert my pressure to ATM, we had that list of, get my one-pager out here, the list of pressure conversions here, so I might need to use that from the last unit. So this one says the pressure of an automobile tire is 1,430 torsellis at 25 degrees Celsius. So those 2 numbers are tied together. What is the new pressure? So new pressure is P2. If the temperature increases to 37 degrees Celsius. So already I know that that's T2. Those 2 numbers are together, which means that this is P1 and this one is T1. Once I know all of my variables, I need to make sure that I have the correct units. Pressure always has to be in ATM. Temperature always has to be in Kelvin. This one is not. I have torsellis. I'm going to have to convert that into ATM, atmospheres, before I do the math. So you have 1,430 torsellis, 760 torr in 1 ATM. So in order to do that math, I'm going to grab my calculator. This number has 3 sig figs, so I need 3 sig figs in my answer, so you get 1.88 ATM. That one is my P1. That's that number right there. T1 has to go to Kelvin, so 25 plus 273. You get 298 Kelvin there. And then 37 plus 273, you get 310 with a decimal place at the end to rescue those sig figs with a K for Kelvin. So now that I have everything that I need, I'm going to plug it in. P1 over T1 is equal to P2, I'm solving for that one, over T2. In order to get my correct answer here, I have to cross multiply. So 1.88 times 310 is equal to 298 times P2. To get P2 all by itself, I'm going to divide both sides by 298. Pen is almost dead. So 1.88 times 310 divided by 298. 3 sig figs, 3 sig figs, 3 sig figs. My answer is going to have 3 sig figs. You get 1.96. I'm solving for pressure, so the unit is ATM. We need to see if that makes sense. The pressure is the one that I'm looking at. It's starting at 1.88. I want to know what my new value is. I got 1.96. My temperature increased. So we're holding our volume constant. When my temperature goes up, so does my pressure. And that's exactly what happened there. So that answer makes sense. The next one, it says helium gas is in a 2-liter cylinder under 1.12 ATM of pressure at 35.5 degrees Celsius. The same sample, so I still have the 2 liters is all that means, has a pressure of 2.56 ATM. What was the initial temperature of the gas in the cylinder? Initial temperature is T1. I don't know that. So this one has to be T2. It says helium gas is under 1.12 ATM of pressure. So that one's going to be P1. And then this one, the T2, the pressure is 2.56. So P1, T1, P2, T2. I need to check my units. That is extra information. I can ignore that. ATM is good. That's in atmospheres. 35.5 plus 273. This value right here is 309 Kelvin. ATM is good, and then I'm solving for T1. So now that everything has the correct unit, and I know all of my variables, I'm going to plug it in. P1 over T1, I don't know that one, is equal to P2 over T2, and now I'm going to solve for T1. How I solve for T1 is by cross multiplying. 1.12 times 309 is equal to T1 times 2.56. To get T1 all by itself, I'm going to divide both sides by 2.56. So now to get my answer, I'm going to take 1.12 times 309 divided by 2.56. This number is 3 sig figs, 3 sig figs, 3 sig figs. So I'm going to round my answer to have 3 sig figs. So I get 135 Kelvin for an answer. So looking to see if this makes sense, my pressure is increasing. I'm holding my volume constant. Sorry, I was reading. So I'm holding my volume constant. My pressure is increasing, so should my temperature. Temperature was at 135. It goes up to 309. That makes sense. So if you guys have any questions, make sure you reach out. Otherwise, I hope that you have a great day.